Okay, so now we're going to simplify a cube root, all right? So the directions read, assume the variables represent positive real numbers and simplify the radical expression. All right, let's get to it then. Um, we have here the cube root of 192, x to the 8th, y to the 12th, z to the 16th. What I'm going to do first is I'm going to look at the coefficient, and I'm going to ask myself, is there a factor whose cube root is a counting number? Now here I have a list of perfect cubes. These numbers on the left here, 8, 27, 64, 125, 216, all the way up to 1,000. There are, of course, perfect cubes larger than 1,000. There are infinite number of perfect cubes, but I just made this list up to 1,000. The next one would be whatever you would take the cube root of to get 11. All right. So these are numbers, at least the first 9 of them, these are numbers for which the cube root is a counting number. 8, 27, 64, and so on. So I just need to know if one of these numbers, one of these perfect cubes, is a factor of my number, 192. And it turns out that there are quite a few, actually, um, cube roots on this list that are factors of, or cubes that are factors of 192. For instance, one of them is 64 and the other one is 8. Both 64 and 8 go evenly into 192. But the one that we actually want is the largest one. So we're going to take the largest factor that's on this list of perfect cubes. And that means that we can write 192 as 64 times some other number, that other number being 3. So that means I can rewrite this. I'm taking the cube root, and instead of writing it as 192, I'm going to write it as 64 uh, times 3. 64 times 3, because 64 times 3 is the same as 192. The product gives you 192. All right, so everything else will stay the same because all I'm doing now is I'm looking for any factors of the coefficient of the radicand that are perfect cubes. So I found a perfect cube, 64. I found the largest one. I always have to get the biggest one. And once you have the largest one, you factor it into that factor and another, and everything else stays the same. So moving along. All right, so the next thing I want to do, once I have this factored this way, the next thing I want to do is I want to go ahead and ask myself this question. Is there a factor whose exponent is a multiple of 3? All right, well, now I'm going to address all these variable factors now, all the variable factors. Well, let's see. Look over here, you see that the cube root of x cubed is x, x to the first power. The cube root of x to the 6th is x squared, x to the second power. The cube root of x to the 9th is x to the third. You find that by dividing. If you divide 9 by 3, you get 3. So that's why the exponent is here. 12 divided by 3 is 4. 15 divided by 3 is 5. 18 divided by 3 is 6. But you notice, in order for this to work, these numbers have to be multiples of 3. So I'm asking now, is there a factor of x, y, or z? Is there a factor whose exponent is a multiple of 3? And the answer is yes in all 3 cases. So let's go ahead and take a look here. So we're still going to have this cube root of 64 times 3. We're still going to have all of that. But now let's take a look at the x. With the x, I'm looking for a factor of x to the 8th that's on this list over here, where the exponent is a multiple of 3. Um, I know that if I take this to be one of my factors, x to the 6th, because both x to the third and x to the 6th can be multiplied to give me x to the 8th. I'm going to take the largest one. I'm going to take the largest one. The largest one is x to the 6. So I'm going to take that factor x to the 6 because I know I can take the cube root of x to the 6 is x squared. And the other factor, if I want to multiply and get x to the 8th, the other factor would have to be x squared, because when I multiply it, I'd have to add these two exponents together, and 6 plus 2 would give me 8. All right, now I'm going to do the same thing for y. All right, now for y, well, let's see, it's y to the 12th. Well, y to the 12th, 12 is a multiple of 3. So therefore, the factor here that has an exponent that's a multiple of 3 is y to the 12th itself. So y to the 12th is a factor that has an exponent that's a multiple of 3. Exponent, we're looking for the factors that have exponents that are multiples of 3. And let's say z to the 16th. Well, z to the 16th, 16. Anything smaller than 16 could be multiplied by something else to give you 16. So let's see, x to the 15th would work, x to the 12th, x to the 9th, all of them underneath would work. X to the 15th, though, would be the largest one that would work. Well, we're talking about z, so it would be z to the 15th. So z to the 15th would be the largest one that would work. This is too big. It's bigger than 16. So here we go. I'm going to take z to the 15th then. Z to the 15th. And the other factor, if I wanted to get this to have a exponent of 16, would just be z to the first power. Z to the first power, all right? So everything in red is something that I can actually take the cube root of. And everything in black are those things that the cube roots are not on one of those lists that we looked at, all right? So let's see. Let's go ahead then and look at the next thing. Next thing we want to look at is the product rule for radicals. Now, what the product rule for radicals does is it allows us to break this radical up into as many factors as we need to. So this says if you're taking the nth root of a multiplied by b, you can just, that's going to be equal to the nth root of a multiplied by the nth root of b. So I split this one radical, this one nth root, into two. And you can actually do that for as many factors as you want. So you see here I have 1, 2, 3, 4, 5, 6, 7 factors. So this rule actually says I can split this up into 7 different radicals. Let's see, the first radical would be the cube root of 64. I know that one. The next radical would be the cube root of 3. That one is irrational. That one I can't really tell. Um, the next one is the cube root of x to the 6. Cube root of x to the 6. That one I know the cube root of. And the next one is the cube root of x squared. That one I'm kind of fuzzy on also. Right? Next thing is going to be the cube root of y to the 12th. Cube root of y to the 12th. And then the cube, I know that one too. And then the cube root of z to the 15th. Cube root of z to the 15th. And lastly, we'll have the cube root of z. The cube root of z. All right, well, let's see. Now, I actually know some of these cube roots. Some of these cube roots I actually know. Let's see, which ones do I know here? I know the cube root of 64. The cube root of 64 is 4. So I know that one. I know the cube root of x to the 6 because 6 divided by 3 is 2. So that's x squared. I know, so that's that one. I know the cube root of y to the 12th because 12 divided by 3, well, 12 divided by 3 is 4. So that's y to the 4th. And I also know the cube root of z to the 15th because 15 divided by 3, 15 divided by 3 is 5. All right, these other ones are things that I have to keep underneath a radical. I don't understand, or I know the cube root of 3 is a number, but it's an irrational number. So I'm going to keep it under this radical, the cube root of 3. The 3 is going to stay under the radical. This one also, the cube root of x to the second. So 2 is not a multiple of 3, and it's smaller than 3, so I'm going to keep this under here, an x squared. And the last one, this one, the cube root of z, well, I'm going to keep z under here also. And here we have everything. So we have the cube root of 64, 4. The cube root of x is 6, x squared. The cube root of x, y to the 12th, y to the 4th, and the cube root of z to the 15th, z to the 5th. And then everything else, all the stuff in black, the 3, the x squared, and the z, all of that goes underneath the radical. And that's how we're going to simplify cube roots.